Welcome to the class of material selection for mechanical design. We are at the final stage of crystal structures role. Okay. In the last stage, what we have said, that how to quantify the density or the packing of atoms, because we said that that will kind of determine that how the slips or dislocations will travel, how the failures will happen, how a structure will be more ductile or not, how we can determine. Now, I have not said what are these kinds of defects or failures. Okay? I have only said that how the atomic packing is going to affect it. But now we are going to talk about what are these defects that are possible in a crystalline structure. So, these that I will be talking about will be mostly keeping the materials like metals in mind, but also some of the ceramic structures will have a similar kind of problem. So, hence it will be generic for both metals and the ceramics, not for the polymers. For polymers, we will discuss about it separately. Now, the defects that can happen in a crystal structure, because I told you that only metals and ceramics show highly crystalline structure. So, the defects that are possible are actually these four types: point, line, plane and volume. Okay? And how they are going to affect us. Okay? First important thing is that imagine how a crystal is forming. It is forming because of solidification, right. So, you take a molten material and then there will be nucleations there, and these are the sites of new thermodynamic phases, like nucleations are happening and the crystals are growing. Okay. So, of course, when we do these directional solidification, we eliminate at random growth of crystals. We only prefer it in one direction. Okay. Otherwise, the crystals will grow and then crystals will grow and you get a grain structure which will be essentially polycrystalline in nature. So, this is what is generally when a crystalline material solidifies from the molten state, right. Now, what happens during that process? This process invariably will followed by defects, because even if the crystals are highly ordered, but not everywhere it is getting cooled at the same rate. Because of the unevenness of the cooling rate, some part is solidifying before other parts, etc. So, there will be always some defects that will come into picture. Okay? So, there will be always some deviation from the ordered arrangement, and this will be the defect or imperfection in the crystal. And what is most interesting is that these go both ways, that the presence of imperfection may be bad in terms of failures, that the strength may come down. In some cases, it can actually give very interesting good properties also to the material. The concept of alloying may also come up because of it. Okay? So, properties of material, it is safe to say that it is influenced by the presence of imperfection. Mechanical properties of pure metal change significantly when these imperfections are present. For example, long before, it was noted that if a molten iron is getting solidified and by chance carbon goes inside, then there is a higher strength that you are going to get it. Yield strength of copper, for example, pure copper is only 117 MPa, very ductile. But you add some 30% zinc in it, you get brass, the yield strength immediately improves to 200 MPa. So, we should not always say that imperfection is bad. Sometimes if we have the proper knowledge that what impurity we are adding to the system, it may actually help us also. So, this is important, that is why for us to know the type of imperfections and how they play in terms of affecting the behavior of materials. So, we are going to classify the defects in terms of, as I told you, the point defects. Point defects can be of different types, like vacancy defect, interstitial defect, substitutional defect, Frenkel defect and Schottky defect. Okay? We will talk about each one of them. Then the line defect or dislocation, like edge, screw or mixed. Then the plane defects, which are like the grain boundaries, the twine boundaries, and then the volume defects, which are like pores, cracks, etc. These are three-dimensional defects. Okay. So, let us start with the point defects first. Okay. So, these are associated of course with the atomic sites. Now, the very first point defect is called a vacancy defect. When an atom is missing from its regular lattice site, then it is called a vacancy. And impossible to create actually any material which will be free from vacancy. Vacancy will be always there. So, presence of vacancy increases the entropy or disorderliness. If there are more vacancies, then there will be more entropy in the system. Decreases the density of the substance also. If there are more vacancy, you can actually get a lighter structure. The concentration of vacancy increases with two cases. One is when there is an increase in temperature, and another is when there is a decrease in the activation energy. In fact, if you look at the number of vacancy, there is a distinct mathematical relationship where if n is the total number of potential defect sites, then number of vacancies is never equals to the potential, but it is a part of it, and that part is defined by this exponential, and that exponential, if you look at it, QV here is the activation energy, K is the Boltzmann constant, okay, and T is the absolute temperature in Kelvin. Now, we said that as QV is decreasing, okay, then energy required for the formation of vacancy are going to be affected. There will be more possibilities of NV to be forming in the system. And in a similar manner, if the temperature increases, the same thing is going to happen. There will be more possibilities of potentials to be filled up by the vacancies. Okay. So, QV decreasing activation energy and increasing of temperature, both of them can control the vacancies in a system. Now, there can be a case where instead of just vacancy, the atom has to go somewhere, no? So, it goes and jumps somewhere else inside its regular lattice. Okay? So, it is like crowding some place. So, this is called a self-interstitial defect, that it is not only vacant, but it is going and jumping into some space, creating a local distortion. Okay? So, this creates a relatively large distortion and strain, and once this happens for not the same atom, but a foreign atom, then it is not self-interstitial, but it is simply a interstitial site or an interstitial defect. Okay. So, like carbon forms an interstitial solid solution when added to iron, and in this case the distortion will not be much because carbon's atomic radius is much smaller, 0.071 nanometer. So, it goes easily inside the space of two big iron atoms, inside space it fits inside. But if it is a self interstitial, then definitely there will be a local distortion in the system. It is also possible to have substitution of one atom by another atom, okay? And this can happen when the two atoms are roughly of the similar size. Okay? So, a substitutional defect is introduced when one atom is replaced by a different type of atom, and crystal structure of both atoms, however, must have to be the same, and they should have almost equal electronegativity, so that overall the atoms will try to create a electrically neutral situation. So, the substitutional atom can then occupy under such condition the normal lattice site, and then you get the substitutional defect. For example, copper 0.128 nanometer gets substituted by nickel 0.125 nanometer, and they are both FCC. Okay? So, they can essentially you can say that this is a solid solution, they can form a solid solution, and we take a good advantage of it, like Monel 400 has about 70% of nickel and the balance 30% is copper, and this is excellent in terms of corrosion resistance in marine and chemical environments. Sometimes we also mix it with aluminum and titanium, and then we get a new material called Monel K500, which is hardened also. So, it is called precipitation hardening. So, this is substitutional defect, which is sometimes have a very positive effect on a system. Now, there can be a effect which is called Frenkel effect, which is a combination of vacancy and interstitial defect together. So, occurs when an atom or ion leaves its regular site and occupies an interstitial site, then it is called a Frenkel defect. So, like cations being smaller in size gets displaced to the interstitial voids. Now, no change in the density would occur, but you will have found it in ionic compounds with low coordination numbers, the Frenkel defect. And this is not very important for us, like silver, calcium with iodine or fluorine. You have to have this kind of a ionic bond where the cation and anions can exchange itself. So, it is not important from our strength point of view, but can be important from other points of views, like say the resistance change and things like that. There it will be important, the Frenkel defect. Another defect that is possible is called a Schottky defect. This is associated with a paired set of cation and anion vacancy, and the density of the solid in this case, however, will be decreasing. And this is found in ionic compounds, not in metals, but in ceramic compounds with high coordination numbers. In order to maintain electrical neutrality, the number of missing cations and anions are to be equal in such a case. And for example, in sodium chloride, potassium fluoride, etc. Now, of course, I told you in both the cases of Frenkel and Schottky, no change in electrical neutrality of the crystal will happen. Okay? So, it is always going to happen as a paired set of a system. There is also another very interesting case of point defect. It is called Wigner defect. This of course happens when there is a nuclear radiation, and in such a case some of the atoms will be displaced because of this nuclear radiation, and since this can happen for any of the cases. So, most important for cases where nuclear moderation can be done, such as in graphite. Okay. So, you have to have of course enough energy in order to cross that threshold that the radiation power can shift a particular atom from its location to some other location. Okay. Like for a graphite, 1 MeV neutron striking graphite will create 900 such displacements of the atoms. Okay. And so, you can actually sort of take lot of nuclear radiation power this way. So, in this case, Wigner defect is actually good in terms of absorbing the radiation effects, and that is why graphene is used as a moderator. Now, I will talk about the line defects or dislocations, which leads to plastic deformation of a system. So, these are two types, as I told you. The first one is called the edge dislocation, and this is nothing but when you have introduction of an extra half plane of atoms. So, you can see here that till this point everything was going fine, and suddenly there is this displacement here and a half plane is inserted here. So, this is where is the dislocation that is inserted, and this dislocation line is perpendicular to the plane of the page here. So, the direction and magnitude of edge dislocation can be similar to our Miller index. Here it can be defined with respect to something called Berger vector. So, move around the dislocation line making equal steps in each direction. The vector that goes from finish to start is called the Berger vector, and edge dislocation lies perpendicular to the Berger's vector. So, first you find out what is the Berger's vector that is happening in a system. Like in this case, you can see that there is a slip plane, and then you get the Berger's vector around the slip plane, and the dislocation is perpendicular to the slip plane. So, this is what is a edge dislocation that can happen in a system. Similarly, if there is a edge dislocation is because of translatory movement. Similarly, there can be a rotational movement. So, then it is because of shear, a screw dislocation because of shear distortion. Okay. So, in this case now you have to rotate around clockwise equal steps in each direction, and then this will be the Berger vector. Okay. So, this is a screw dislocation, and as you are moving, the direction of the movement of the right hand screw, that's actually will tell you that how these planes are going to move. So, again a screw dislocation moves in a direction perpendicular to the Berger's vector. In this case, like this is the way the slip plane is going to go and move. Okay, so these are the two types of edge dislocations. Now, dislocations actually reduce the strength. Okay, so if you use single crystal, it is expensive, but it is something that for turbine blades you always try to do. Okay, so no grain boundary, so that single crystal, so no possibility of a dislocation. Dislocation can only happen when there are multiple grains and then you are having these half grains or rotations that is there. The other way to avoid dislocation is work hardening. That means these you actually move all the dislocations out of the grain boundaries. Okay. So, this is another technique, okay, that we use, the work hardening technique. And another way to capture the dislocation is introduce an impurity. So, we call it pinning of the dislocation. That means that impurity, as it goes inside, it stops the movement of the dislocation. So, these are different ways by which we can control the dislocation. Now, we come to surface or the planar defects. Okay. So, these are associated with the grain boundaries. So, a boundary separating the two grains or crystals having different crystallographic orientations in polycrystalline materials. So, this is where you can have the presence of defects due to the angle of misalignments. Okay. So, this is a high angle grain boundary, let us say, and this is a small angle grain boundary. So, these boundary, how they are relatively oriented with respect to each other, and whether there is any large distortion or not, that actually define the chances of the defects propagation between the two grains. Now, naturally a grain boundary has in a 3-dimensional situation, it has 5 degrees of freedom, considering with respect to a grain how the other grains are moving. So, we need 3 dop to define the orientation of one grain with respect to the other, and 2 dop to specify the orientation of the boundary with respect to one of the grains. So, we get total 5 degrees of freedom from the grain boundaries. Now, the grain boundaries play a very important role. For example, using grain boundary, you can create an obstacle to dislocation. I told you in work hardening, that is what happens. At high temperature, they tend to weaken materials as grain boundary sliding may occur, and this is why we try to avoid it for a creep problem. And in general, fine grained materials are stronger than the coarse grained materials. Why? Because then the chances of this this angle of misalignment, like a high angle grain boundary, will be much less for a fine grained material. So, grain size distribution is very important. Okay. So, there is a standard ASME standard n number, and that is defined as 2 to the power small n minus 1, where small n is the grain size number. Okay. And then you can find out from this the capital N, which is the average number of grains per square inch at a magnification of 100x. So, that is the way through a kind of a microscope we define that what is the grain size of the system, and then accordingly we define that whether it is of a fine grain or a large grain material. So, like you see here, there is a small problem that determine the ASTM grain size number of a metal specimen if 45 grains per square inch are measured, okay, at the magnification of 100x. You have to always do it at 100x. Magnification changes the number of counts. So, using STM method, then your n is 2 to the power n minus 1. So, you can take logarithm. So, n will be log n over log 2 plus 1, and then that it is 45 grains. Okay. So, you will be able to find out that actually the number of grains, okay, corresponding to this ASTM grain size 45 is 6.5. Okay. And then if you want to do the other way, that for the same specimen, how many grains per square inch will be there at a different magnification, 85x, let us say. So, now you use the equation first of all to find out what is the Nm grains at a magnification m, and then you use the 6.5 and 85 in order to get the 62.6 grain per square inch at 85x. So, thus you change the magnification number, and then how many grains you are expecting, you can accordingly calculate. So, that is a very important way of identifying the grains. Now, let us talk about the slip systems. Okay. So, slip system is nothing but a combination of the slip plane and the slip direction. So, slip plane is generally taken as the closest packed plane. I told already to you that it is the closest packed planes which is more susceptible to slip, and slip direction is the direction on the slip plane with the highest linear density. So, for example, FCC has these 111 family planes which are the slip planes, and as each plane contains 3 of the family of 1002 direction, it is going to have total 12 slip systems. The more the slip system, the higher the possibility of ductility of the material. BCC will have 6 planes, and then 2 of them are only the directions. So, this also will have 12 slip planes. Okay. However, for BCC, the slip plane is not the only thing. You will see that the linear density for this is quite smaller, and hence it is going to get more, it needs more energy to actually make it ductile. Okay. So, only slip plane is essential, but not a sufficient condition, the number of slip planes. HCP can be defined because HCP has only 3 slip systems and they are quite brittle. So, low slip plane invariably would mean that the material would be brittle, but it is not sufficient condition. You have to also look into that what is the linear density, okay, and then together you will be able to actually decide whether it will be a ductile material or not. Now, another important thing in terms of crystals is the twining of the crystal. Okay. So, this occurs on definite crystallographic planes, okay, where each plane is basically the mirror image of the other plane. Okay. So, this can happen in mechanical twin, like using shear forces, occurs in metals of BCC and HCP crystal structure, and then there can be annealing twin, that is deformation due to heating and cooling. Okay. So, one particular material which shows this twining and plays a very important role in the memory is called the shape memory material, where it is an alloy of nickel titanium, and if you actually from the parent state, austenite, if you cool it, then you will get these self adjusting states or the twine states. Okay. So, at the martensite state, and this happens for the shape memory alloys or SMS. Okay. So, twining plays a very important role in terms of defining the memory effect, whether a material is going to have memory or not. Usually in such a case, these twining it will make it highly deformable, you can deform it, and then if you heat it back, it goes back to austenite and it remembers the exact shape. So, of the 3 common crystal structures, BCC, HCC, FCC and HCP structure is most likely to twine generally, but FCC and BCC structures will not usually twine because slip is more energetically favorable. Twining occurs at low temperature and high rates of shear loading condition, and there are few slip planes present. So, either there will be slip or there will be twining, and it is, if there is slip is less, invariably the chance of twining will increase, and small amount of deformation when compared with slip, but of course it becomes very flexible and you can then largely deform from twining to detwining of the system. Now we come to the final one, that is the volume or the bulk defects. These are large and undesirable situations because this is going to create pores, okay, like gases trapped during solidification, cracks, improper shrinkage, or foreign inclusion and other phases. So, they are almost always undesirable because they decrease the mechanical strength and promote fracture of a system. As you know, for example, I have given you that example of chalk, that the chalk is a very porous material, and hence its strength, you have to use a Weibull modulus to actually see that its strength varies a lot. Okay. So, porous materials always has this problem, but however, having said this, porous materials can be good in certain other cases. For example, porosity makes it lighter. So, if you want to decrease these weight, it is good. Secondly, porosity can actually help, like for a ceramic material, to make it sustain more high temperature. Okay. So, that way porosity is good, that a high thermal resistance you can get. In some cases, you can actually fill up the pores with materials like say viscoelastic materials. Then you get a very interesting property of a large damping. So, then a porous material is good if you can absorb a secondary phase inside a porous material. So, thus there are always chances of improvements for a porous material. Now, I am going to summarize whatever I have talked about. Okay. So, first of all, we have talked about vacancies, and the properties it is going to affect is solid state diffusion and mechanical creep. So, application in annealing. Substitutional is going to affect electrical conductivity and mechanical strength. You can actually make a solute hardening of alloys using this, and also you can create semiconductors in substitutional system. Interstitial, magnetic coercivity, dielectric strength, optical transparency, all of them are possible, and you can get through this strong permanent magnet, you can build capacitors, coloring of glasses and plastics. So, interstitial is good in some cases. Dislocations or twine boundaries, that can actually help you in plastic deformation, and that can be used effectively for strain hardening. Grain boundaries, if it happens, then it actually affects the dislocation movement, electrical resistance, magnetic coercivity and optical transparency. So, this can be used for mechanical hardening and also in some permanent magnets. Finally, if there are stacking faults, interruption in stacking sequence, it is going to affect the mechanical strength and the electrical resistance. So, thus the defects can play positive as well as negative role depending on the context where we are going to apply it. So, these are the important things from a crystal structure point of view that we have to keep in our mind and accordingly select materials. This is where I will close this discussion now. Thank you.